Okay, so in this video we're going to look at a new property that we haven't talked about before called momentum and its related counterpart called impulse. Momentum is a property that is derived by the product of the mass and the velocity. Simply a property which is defined based on the calculation that you use to make it. It is a property which originates in the second law. The second law is typically expressed as F equals ma, but you'll see a little bit later in this lecture, we'll look at the origin of that, and you'll see that Newton actually, when he expressed the second law, he didn't express it as F equals ma, he expressed it in terms of the momentum of the object. So this momentum of the object very much will help you to understand how difficult it will be to change the motion of an object. An object that has a lot of mass, it's going to be very difficult to change the motion of it. An object which has a lot of velocity, or an object which you want to give a lot of velocity to, it will be difficult to give an object a lot of velocity. And these two products combine together to help you understand how difficult it will be to make an object change its motion. It is a vector property because mass is a scalar and velocity is a vector. And so when we multiply a scalar times a vector, we still have a vector property. The direction of the momentum comes from the direction of the velocity, obviously. The symbol for momentum is lowercase p. And again, it's calculated by mass times velocity. If you think about the units for this, then the units would have to be, for mass, that's kilograms. For velocity, that is meters per second. And unlike the units for force, which were similar, kilogram meters per second squared, these units don't get a special designation. So there's no shorter name for it. It's just simply a kilogram meter per second. Besides the momentum of an object, we will especially, because that's really kind of boring, I mean there's nothing especially interesting about the momentum of an object, we'll be much more concerned about when objects make changes in their momentum. That might be because they collided with something, it might be because a force was applied to the object and caused it to change its momentum, and so as a result we will look a lot at this property, delta p, the change in momentum, and obviously, as with any change in any property, I could calculate that by the final momentum minus the initial momentum. Each of those could be calculated separately as mv for the final momentum and mv naught. For the initial momentum, since the m is common to both of those, we could factor that out. And obviously, this should be familiar to you. V minus V naught is the change in velocity. Most of the time, we'll express the formula for the change in momentum in this way, m delta v, but any one of these four variations, p minus p naught, mv minus mv naught, or m times the quantity v minus v naught, equally good. But this, clearly the simplest notation is to simply write m delta v whenever we want to write an equation for delta p. So we're going to look at both of these just with a couple of real quick example problems, nothing real complicated. Unlikely you would be asked these two questions, but just to give you a sense of how the problems, how a simple problem or simple version of the problem would look. We'll take a look at the calculating the momentum of an object, and then secondly we'll look at calculating the change in momentum. So for the first problem, we'll look at a truck traveling westward at 15 meters per second, and the mass of the truck is 1,200 kilograms. I'm going to write out all the properties that were given to us, and in this case, just simply v, not the final velocity, but just the velocity. And I am looking for p, the momentum. So the formula for momentum is mv (1200 times 15) and that is 18,000. So I will express that as 1.8 times 10 to the fourth to be consistent with the number of significant figures, 2 and 2. And then again, the units are kilogram meters per second, and the direction is west. I might also have put a negative sign in front of here to indicate the westward direction, west typically being considered the negative direction. So I could have just put a negative in there to express that direction also. Pretty straightforward. Very unlikely on an IB exam that you would ever be asked a question that's quite this simple, because it just really requires very little understanding on your part of the significance of momentum, or what momentum actually means. So slightly deeper, slightly more challenging problem would be to look at the change momentum of a problem, of an object, I should say. And so this problem asks to determine the magnitude and direction of the change in momentum of a 0.74 kilogram ball that strikes a wall normally. And normally means perpendicular. And so the ball is coming in at 3 meters per second, bounces back at 2 meters per second. So this one is a little bit trickier in the sense that you really need to be careful about the directional information, because we have to make this calculation of the change in velocity, the delta V part. We really have to think carefully about the direction of these two. So if the ball comes in, strikes the wall, and then bounces back, obviously these two cannot both have the same direction. One of them has to be negative and one has to be positive. As I've drawn this particular picture, which is not stated in the question, but I drew the picture this way, I've drawn the incoming velocity moving to the left, which typically would be taken as the negative one. It doesn't really matter though, so long as one of them is negative and one of them is positive. If you choose the direction to the right to be negative, that's fine. So long as you establish a direction, the direction of the positive and negative, and then stay consistent with that, then your answer will be consistent with what you have established as the coordinate system. So that's your choice. It's not established in the problem as to whether the 3 or the 2 is in the positive direction, but you as the physicist have to establish a coordinate system and then stay consistent with that. So in this case, the mass of the ball is 0.74 kilograms. The initial velocity is -3, and the final velocity is 2. And we are being asked for delta P. So the formula is pretty straightforward. Delta P is equal to m delta V. And we can calculate that. So now I want delta V, and just to remind you, the change in any property is the final minus the initial. So in this case, the final is 2 minus the initial, which is -3, right? And so this 2 minus -3 is going to clearly give me 2 plus 3, which is 5. So what that says is that the change in momentum is pointing in the positive direction. That is correct. The change in momentum is always going to point in the direction of the acceleration. And in this case, the acceleration is to the right. The object was moving to the left, it slowed to a stop, and then continued to pick up speed, moving to the right. That is consistent with an acceleration which points towards the right. Very important. The change in momentum, as a result of the fact that it depends on the change in velocity, and the change in velocity is what determines the direction of the acceleration. Acceleration is delta V over delta T, but T has no information about direction. So the acceleration is dependent on the change in velocity in the same way that the change in momentum also depends on the change in velocity. So delta P and A, the acceleration, point in the same direction. And in this case, as I've drawn my picture, the calculation of the change in velocity says that the change in momentum points to the right, which does make sense. The object was moving to the left, but it ended up going to the right, so clearly there must have been something that changed its momentum, and that pointed towards the right. So in this case, we get an answer of 3.7 kilogram meters per second. So that's a pretty straightforward problem, not terribly difficult. It's just the issue of keeping track of the positive and negative in terms of the delta V. Do the velocities, they could point in the same direction. You can imagine a car traveling and then gets struck from behind and picks up speed. It's not a requirement that the velocities have to point in opposite directions. You just simply have to pay attention to the context of the problem to decide whether this is a situation where one of the velocities needs to be negative. So let's look at a little bit more complicated counterpart to momentum called impulse. So impulse is also a vector quantity, and it depends on the product of the force acting on a body multiplied by the time that that force acts on it. Ultimately, what is important for you to make the connection is that impulses cause the momentum of objects to change. That's what we're going to really be concerned about. We're going to look at how forces applied over some period of time caused an object to change its momentum, or that is to say, to change its velocity. It's easy to sort of see where impulse comes from if we return back to our earlier explanation of the second law. Right, so the second law is often expressed as F equals ma, but just to remind you, that sort of hides things. Now, Newton did not express the second law as F equals ma. Newton expressed the second law in a slightly more complete way, and that is that F was equal to, and he conceived of any of the three properties that make up ma, that is the mass of the object, the change in velocity, which is hidden in the acceleration, and the change in time. Now, obviously, if we don't have a change in time, then we have no problem, right? But he conceived of the idea that both the mass of an object and the velocity of an object could change. You can imagine, for example, if you blow up a balloon and you let the balloon go, then the balloon starts to fly around the room. The mass of the balloon is changing, it's decreasing, it's applying a force to it, and as a result, there is an impulse. It changes its velocity over the period of time that the air is exiting the balloon. So he thought in a little more complete sense. Now, for our purposes, we are rarely going to look at an object in which the mass is changing. We'll, for the most part, stick with objects where the mass is not changing, which means that this equation would simplify down to and while if we connect the v and the t, we get the acceleration, but if we connect m and delta v, then we get delta p. M delta v is the change in momentum. So Newton's expression of the second law was that F is equal to delta m delta v over delta t. And as a result, you can see that the change in momentum can be calculated through this new method. Instead of using m delta v, it could alternatively be calculated by calculating F delta t. And, or then in other words, that is to say that F delta t is equal to delta p. So Newton identified two new properties through the second law. One of them was the change in momentum, and hence we have this term called momentum. If you have the change in momentum, then there must be a property called momentum. And another property which he referred to as the impulse. And clearly you can see that the impulse is equal to the change in momentum. And I think that just in a conceptual manner, the way you want to think about it is that impulses are what are causing the change in momentum. If you apply an impulse to an object, then you will change its momentum. When you use the word impulse, you can use it in the same context that you use forces. So for example, you can say that a force is exerted. You can also say that an impulse is exerted. You could say that an object or a body experienced a force. You could say that an object or a body experienced an impulse. Impulses can be delivered in the same way that a force can be delivered. You might talk about the agent of the force. Who is the agent of the force? Is it gravity? Is it the friction? Is it the thrust? In the same way, you can talk about the impulse. Who is the agent of the impulse? Because the force is the part of the calculation for impulse, much of the same language that we use for force, you can use that same language for impulse in sort of the same context. Just to verify that the units are the same for these two things, because they do certainly look different superficially. On this side, the units for impulse units are newtons times seconds. So that's a little bit of a new unit. We haven't seen that before. So a newton second should be equal to the same units for the change in momentum, which was the kilogram meters per second. So just to verify that real quickly, just to remind you that a newton comes from mass times acceleration. So therefore that would be a kilogram meter per second squared multiplied by s. That should be equal to kilogram meter per second, and obviously you can see that it is. So kilogram meter per second is equal to a kilogram meter per second. It's important kind of conceptually to understand that the units are the same, but there is sort of an appropriate place for using those units. So if you are asked to calculate the impulse, and it isn't uncommon, I would say I have seen it before, where the letter I was used to represent the impulse. The letter I also represents another property called the moment of inertia. And so in general, I don't use the letter I to represent inertia. But if you did, if you said that I was equal to delta F, or F delta T, it wouldn't be wrong. It would be understood what you were doing. But for our purposes, I will always express, when I'm asked to calculate the impulse, I will simply write out F delta T. The units for impulse are newton seconds. The units for momentum are kilogram meters per second. They are equivalent. They are the same thing. So if you were asked for impulse and you wrote your answer in terms of kilogram meters per second, that would be totally correct. There's nothing wrong with doing that. But it's a little odd, and I would use this analogy. So if you imagine if you bought like a small piece of candy, let's say the piece of candy cost 10 cents. So if you express the cost of that candy in dollars, it would be a little bit odd, because the cost of that would be $0.1, right? And then conversely, let's say you bought a shirt and the shirt was $25. You could say that the shirt cost 2,500 cents. That's completely correct. There's nothing wrong with doing it, but it's a little odd. It's just not the conventional way of expressing it. So when typically we talk about the cost of something that is very small, it makes more sense to use the number of cents that it costs. And when we're talking about something that has a larger cost, then we typically use dollars to express that, even though there is an equivalence to them. There is an equivalence to those. There's an equivalent way to express any number that is given to you in dollars can be expressed in cents, and any number given in cents can be expressed in dollars. Similarly, same thing with impulse and momentum. But conventionally, impulse since the equation for impulse is F delta T, it typically would be given in newton seconds, and anything with momentum or change in momentum would be kilogram meters per second. So just something to keep in mind when you're being asked to solve something. As to which units that you choose, you can't really make a wrong choice, but it is a little awkward if you pick the wrong one. So I would like to look at two problems that involve impulse. I'd like to start with a kind of a simpler problem, and then we'll go to a little more complicated problem that is probably more likely what you would see if you were to encounter this on an exam. So let's take a look at a very popular sport, soccer, in which impulses are delivered constantly. Every time somebody kicks that ball, there's an impulse delivered to it. Every time the ball bounces off the ground, there's an impulse delivered to it. Every time somebody catches the ball, or the ball bounces off of the goal, off the frame of the goal, there's an impulse delivered to the ball. So that's an excellent place where you can see impulse in action. So in this case, I'm just going to start reading the question and pulling out some of the given information. So the soccer player kicks the 0.4 kilogram ball, which is the mass of a typical soccer ball, which is initially at rest with an average force of 215 newtons. It's a pretty fair amount of force, but just to remind you, the weight of a average soccer player is probably around 700 or 800, maybe 900 newtons. And it was over 0.056 seconds. So typically when you solve impulse problems, they are going to be forces that are exerted over very short periods of time. They don't have to be exerted over short periods of time. I could, for example, take a cart that was on wheels, and I could push that cart for 10 seconds. And as a result, the force multiplied by the time would tell me the impulse and would allow me to think about the change in the momentum, how fast the cart was going at the end. But it is much more common when using impulse to use it, and it's especially helpful when the forces are applied over very short periods of time. So in this case, I'm being asked to calculate the total impulse experienced by the ball. So that's the F delta t from back up here, the F delta t, and then also to determine the final velocity of the ball. So we'll start again by calculating or looking at the initial quantities here. This is equal to 0.43 kilograms. I was given the initial velocity, so that's a little hidden in there. So it said the ball was initially at rest. The average force was 215 newtons, and the time, delta t, is 0.056 seconds. I'm asked for two properties. First, I'm asked for F delta t, and then lastly, I was asked for the final velocity. Okay, so I have the force and the time, so obviously the impulse, that's a pretty straightforward calculation. So F delta t is just simply the 215 newtons multiplied by 0.056, which would give us a value of so that is 12.04. And just to remind you, the units, since I'm calculating impulse, would be Newton seconds. So I would say that F delta t was equal to 12 Newton seconds, just to be consistent with the significant figures. I don't know anything about the directional information of this, so I will assume that this impulse was positive, that the impulse was delivered in the positive direction, since there's nothing in the problem that would give me any indication about what the direction of the impulse or the force. So then secondly, it asks you to determine the final velocity of the ball, and we know that F delta t is equivalent to the change in momentum, and that is mv minus v naught. But in this case, we were told that the initial velocity was 0, so it actually simplifies down even a little bit more. So F delta t would just simply be equal to mv in this case. That means that the final velocity is F delta t over m, moving the m over to the other side. And so therefore, and this is really important that you don't recalculate this. I'm not going to put 215 times 0.056 because I've already calculated the answer to that. The answer was 12. I simply need to bring in the time information. That was over 0, not the time information, I'm sorry, the mass, which was 0.43. And so, I'm sorry, my bad. So that would come out to be 28 meters per second. This is I would consider to be a relatively low-level problem. You were given everything that you needed. You just walk through, and you just keep adding the missing pieces as you work your way through. It's a good problem, but relatively, I think, like kind of low level, maybe barely above a level 1. Something would be a little bit more challenging, would definitely be clearly a little more of a level 2 problem, would be the following. And the kind of problem that you're much more likely to run into in an IB exam would be the following problem. So in this example, an 850 kilogram car brakes suddenly, reducing its speed from 25 meters per second to 10 meters per second over 1.35 seconds. So you're asked for two properties again, just like you were in the last one. The impulse that was delivered to the car, but this time, instead of asking you for the final velocity, which is clearly given, you're asked to calculate the average braking force. So just looking at what was given in the problem, I have the mass of the car. I have the initial velocity, which was 25. I have the final velocity, which was 10. Both of these are either both in the positive direction or both in the negative direction, but they're certainly both in the same direction. And then I'm given delta t. And I'm asked for the impulse, which is f delta t. And I'm also asked for the average braking force. Okay, so here's the problem with this one. The formula for impulse is f delta t, but I don't have f. In the given information, I don't have the force. Now, it's very common, I find, for students to see that mass and immediately know that they could calculate the force, called weight, by simply multiplying by gravity. So they multiply by 9.8 or they multiply by 10 to come up with a force of approximately 8,500 newtons. While that is true, that is a force, it's not the force that is delivering the impulse to the car. The impulse being delivered to the car that causes this change in velocity, and therefore this change in momentum, is being caused by the braking force, or more to the point, the frictional force between the tires and the road. So while I can certainly calculate a force, calculating the weight of 8,500 newtons and then plugging that in and multiplying that by t would not give you the correct answer. And it shows a really conceptually a lack of understanding of what impulse means. Impulse is not just any random force multiplied by the time. It's that specific force which caused the change that you were looking for. And in this case, there's no change in the car vertically. The car is not moving up or down. It's not accelerating up or down. There's no change in the car vertically. That's the only way that the gravitational force, the weight, could deliver an impulse, is if something was happening vertically to the car. So if, for example, something is dropped onto the ground, then gravity can play a role in the impulse. But in this case, it is most certainly not causing any impulse. So here's the trick. While I don't have the force in order to be able to calculate the impulse, I do have the mass and both of the velocities. So that means that the right side of this equation, m delta v, I have this side of the equation. So instead of multiplying force times time to come up with the impulse, I'm instead going to calculate the change in momentum. And so in that case, that would be 850 times, so in this case, final velocity 10 minus initial velocity 25, to give me an impulse of negative 12,750. And again, this would be Newton seconds. I would simplify that, not simplify, but stay consistent with the significant figures. That would become 1.3 times 10 to the 4 Newton seconds. Okay, so the equivalence of the change in momentum to impulse allows me to calculate one without actually knowing the values of the properties that make up that particular thing. So impulse is based on force and time, but if I don't have that, I could use the mass and change in velocity. And then conversely, I could, if I didn't have the change in velocity, for example, I could still calculate the change in momentum if I knew everything about the force and the amount of time that force was applied. Very, very common type of problem. A little bit higher level and something where you have to show your understanding of the equivalence between impulse and the change in momentum, or the idea that the impulse is what causes the change in the momentum of a car. So now that I have this information, I can calculate the average braking force, because I can just simply go to this statement right here and see that F delta T would be equal to minus 12,750 divided by delta T, just doing the algebra. So minus 12,750 divided by, the time was 1.35. Apologize. And so the average force So this is 9,444. And so to be consistent with the significant figures for the information that was given to us, we would say that the average force was minus 9.4, and in this case times 10 to the 3 newtons. Since we divided by time, the Newton seconds now simplifies down to time. And just for the record, this guy would have been negative also. Not super relevant for the problem, but it is taking away from the momentum. So the impulse is negative. It's taking away from the momentum, not adding to the momentum, based on the context of the problem. So I was able to calculate the impulse by looking at the change in momentum. Once I had the change in momentum, then I could fill in the only other thing that I was missing from that equation, and that was the average force. Really important to understand that this is only telling me the average force. If the force was fluctuating, there's no way for me to know that from this problem. And it's very likely that it was. In general, the braking force is not a consistent force. When you hit the brakes, initially the force is a little smaller, and as you push harder on the brakes, the braking force increases. And it may actually even decrease if you push the brakes too hard, actually. So all I can get from this formula is the average force. Okay, but if you ask me, let's say 1.2 seconds into the braking, what was the actual force? I couldn't tell you. I could not tell you what the actual force was, because there's not enough information in the context of this problem to be able to give me the instantaneous value of the force, but I can give you a very accurate measure of the average value of the force. So that gives you just a basic overview of momentum, the change in momentum, and then the related counterpart, impulse. In the next video, we will look at another related topic to these called conservation momentum, where we'll look a lot at collisions.